Hey guys, welcome to chapter 2.6.2 of modeling equations. This subsection is going to be the same type of problems as 2.6.1, except we're going to be dealing with area rather than just plain distance formula. So let's say we have this upside down parabola, and then we have inscribed within it a square. And so we're going to say this point right here is going to be point xy. So the question will ask you, in terms of x, meaning the equation can only have x's in it, one variable, what is the area of the inscribed square? So in the previous section, we did the distance formula to measure the distance between a point and a different point on the graph. So for this one, since we're going to finding area, you have to write your general equation. That's your first step. So we'd say A equals x times y, because the area is going to be this length x times this length y. Now we know we want this only in terms of x, so we'd write A of x equals x, and then instead of using y, we want to plug in the equation for y. So let's say this problem gave us that this parabola right here was, the equation was y equals 25 minus x squared. So that's your equation. So now we know that these two are interchangeable, y and 25 minus x squared. So what we can do is we can have x times, and then instead of y, we can write 25 minus x squared. Simplify that down, get a of x equals 25x minus x cubed. So this is what you call your model, as we went over in the previous section. So this is your model. You can now use this to find the area of the inscribed square at any point x along the parabola. So next, the problem's most likely going to ask, what is the domain of this function? And the domain is important to know for two reasons. The first being to graph on the calculator. When you plug that equation in on your graphing calculator, to properly view the function, you're going to need to set an appropriate window. So when you go on your calculator to window, you're going to see x min, x max, y min, y max. So if you get the domain down, you can pretty much figure out how to set your window to appropriately fit all the values of x that the function can have. The second reason is to know the limits of the model. You want to know what values of x you can plug in and get a return y, or in this case, you can get an area. So if x is a certain number, you won't actually get an area, so you need to know which values of x you can use. So in this problem, we don't want to have negative area, and you'll get a negative area or no area if this equals less than or equal to 0. So as this stretches out and we use larger and larger x values, as we pass this point, you're going to start to get a negative area. And so we don't want that, so that's why we're going to set a domain. So to set the domain, we're going to set this function equal to 0. So 0 equals 25 minus x squared. You can rewrite that as x squared, or we can do not equal domain. So x squared cannot equal 25. So x cannot equal plus or minus 5. So plus or minus 5 would be your domain, except we can see that this function is bounded by the x and y axes over here. So we know that x cannot actually be less than 0, less than 0. So x has to be greater than 0, but it has to be less than 5, because 5 is going to be right here. So past that point, we're going to have negative area. So you could write that one of two ways. X such that x, or at 0, like that, x is less than 5 or greater than 0, or you could write it, I actually use this notation more often because it's pretty simple. You can just say the domain is from 0 to 5, and then the parentheses means non-inclusive, so it can't be 0 or 5. And so that's it for domain. And that's any values in between 0 and 5, not including 0 or 5, will give you a positive area for this problem. So the next problem, the last problem, would probably ask you to find the maximum value. So at what point in x are we going to get the maximum area? Is this area going to be the biggest? So we have our equation a of x equals 25x minus x cubed. So that's our model. Remember, that's our model for area in terms of x. So this problem is basically all calculator. It makes it pretty easy since we just did the domain, so we can actually set our window to be your x min. Your x min is going to be 0, your x max can be 5. So yeah, just match up the window with the domain we just did, so it'll give you a nice little graph. And so you type in this equation into your calculator, and you graph it. I actually made my y min 0 because you know it's all positive, and the y max, you can kind of just play around with it, see which one incorporates the graph. For this one I did 50, and it worked pretty well. After you graph it, you should get something that looks like this over here, if you have an appropriate window. And so then you're going to hit second and then the trace button, so second calculate, at the top of your calculator, and you can go down to number 4, which is maximum, and then it'll ask you left bound, which you can see the maximum is probably right here. So it'll say left bound, choose some value over here, and click enter, and then it'll say right bound, choose some value over here to the right. So just scroll over and then hit enter as well, and then it'll say guess, and you can just hit OK, or you can move it close as you can, your best guess. Hit enter, and it'll pick a point for you. So in this case, it ended up being about 2.89 and 48.1. So that's your maximum value. So what these coordinates actually mean is that when x is 2.89, you're going to have your maximum allowed area of 48.1. So area is 48.1 when x is 2.89. And so that's pretty useful to know if this was a real world problem. You want to know how much of x you need, whatever your independent variable is, to achieve your maximum area. So now we're going to do a practice problem from the book. It's a little bit more complicated of a problem. It's going to be on page 115, number 9. So here we have a square inscribed within a circle. The equation for the circle is right here. X squared plus y squared equals 4. So we know it has a radius of 2. 1, 2, 1, 2, 1, 2, 1, 2. So, and you can see here that there's a point xy, which is where these two touch. So we know we can relate the area of this inscribed square in terms of x using the equation we have for the circle, like we did in the previous problem. So there is one main difference here. You remember the first step is when finding area, the first step is to write your general formula. So in this case, it's not actually x times y, because x is this distance, x is this distance and y is this distance. So x times y would give you the area of this little corner. So you could do 4x times y, and that would give you this and all of these. Or you can think about it, you want to multiply 2x times 2y, it'll still give you 4xy. So let's write that out. We have the equation is going to be 4x times y. We need to do a little work first to get y. So y squared equals 4 minus x squared. Take square root of both sides. Y equals the root of 4 minus x squared. So you can use that, plug that in up here. So we know it's 4x times y. Writing it in terms of x. Get a of x equals 4x times root 4 minus x squared. So write that a little neater. A of x equals 4x root 4 minus x squared. So this is your new model. So we got the equation for area, the model equation for area. Now this problem just moved on and it said, okay, now find the model equation for perimeter. So for perimeter, we can do the same thing, except we're just going to have a different general equation. So let's go to step 1. The general equation for perimeter is just going to be this plus this plus this plus this. So to do that, we're gonna want to say 4x plus 4y, because if you look at it, if you break it down, we have 1x, 2x, 3x, 4x, 1y, 2y, 3y, 4y. So remember, perimeter is just the absolute value. You don't really want to pay attention to the fact that this is going negative and then this is going negative. But in terms of just plain distances, this distance right here is called x, and this distance is also x because it's a square centered at the origin. So that's 2x, and then this is also another 2x, that's 4x, this is y, this is y, this is y, this is y, so 4y. So the general equation is 4x plus 4y. And now we're just going to want to do the same thing as we did last time, replace the y with x's. So if you remember, we broke this one down to y equals root 4 minus x squared. So we can just do the same process. 4x plus 4 root 4 minus x squared. And that's your answer. That one turned out to be pretty simple. So that's your model for perimeter. Alright, p of x. So, yeah, it's pretty straightforward. You just remember to write your general equation, and once you figure that one out, you can just substitute your y for an x's, and just write out your model. So now any value of x it gives you, you could find the perimeter of this inscribed square. So the only tricky part with this problem was making sure you get the general formulas right. This one is not just in your first quadrant like the previous problem. This one takes up all 4 quadrants, so you have to be careful to make sure to account for all those different distances. And so that's it. We'll see you next for 2.6.3, which is the last set of these making your own functions.